equation of delta H naught minus T delta S naught. I'm not sure why it doesn't work if you do it with the sum of the delta G super. So you get a different answer.
Part A?
Yeah.
Okay.
I mean, they're really close, but one of them's negative and one of them's positive.
Then that's not so close.
No, like they're like one is like 0.5 negative, the other one's like 2 positive.
Oh, all right, that's close. If this reaction proceeds to any significant extent at 25 degrees C, so you did this?
Yeah, but that's the one I'm telling you. It doesn't work with the delta G knots adding them for formation.
It should. It should. You know, there's going to be a slight difference because the values of delta H and delta S and the delta G's of formation. And so,
the slight difference means one's negative, positive.
yeah, one's negative, one's positive. But in the overall scheme of things, it's not like it's black and white. In the overall scheme of things, that one that's negative and the one that's positive is going to be, basically what it's telling you is the K is going to be close to 1. And so the one that's negative is just slightly below 1 or whatever. And is that right? Yeah. The one that's positive is slightly above 1. You know, but it's going to be around there. So the equilibrium is going to have significant quantities both. And so does the reaction proceed to any significant extent? Well, it depends on your sorting materials. And if we're at the standard conditions, then it's not going to proceed to any significant extent because it's going to be close to equilibrium. But it depends on, you know, your Q as well. There's all these, although it's going to be 1, 1, 1, 1. So, what did the book say as far as proceeding to any significant extent?
So with that one, it said, I think it said it was going to proceed slightly.
Slightly, okay.
Yeah. Which doesn't make sense since they had a positive value.
Yeah. Yeah, well, if you have a K that's, or delta G, well, if you have a delta G that's, you know, just slightly above 0 or slightly below 0, so it's very close to equilibrium. That is, the standard conditions are very close to equilibrium.
Oh, no. They said because delta G naught is positive, the reaction does not proceed in the forward direction.
Yeah.
At 25.
So on the reactant side a little bit.
And you did the calculation with delta H and delta S.
Yeah, adding them.
Yeah, that's always a headache when that happens, unfortunately. But
Which one do you use?
either one, because you don't know which one's more accurate, and so either
Should we
one's fine.
average those two values out?
You could average the two values out. That's another option there.
That's the name.
But normally they're both, you know, negative, both positive. The one's negative, and one's positive. But it's going to be close to equilibrium. All right, Kelly.
Okay, I have a question on number 10?
Number
No,
10.
not number 10, but number 19.
Number 19.
Yes.
Okay, for the mixing of ideal gases, this one? Yeah?
22, sorry. 22.
22?
Yeah.
Scott, did you have a question about this one?
Well, they just assume that the mix gases, and you have to, the idea is like, it's going to be endothermic in order to like,
Expand.
add things together. Oh.
Are they talking about endothermic, like expansion?
I think they consider it to be like synthesis of two. So like you need to add and repeat it to put them together. It's clearly spontaneous. It says, oh, never mind. It says no reaction occurs, so that delta H.
Well, they're ideal gases.
Okay,
They have no
yeah.
interaction or something.
Delta S is positive because gases are more dispersed.
Well, do you guys remember the adiabatic versus isothermal expansion of gases in chapter 6? Remember that?
It gets like colder,
Right, it gets colder because work required to expand the gas. Right, that's adiabatic. Our processes are going to be isothermal because we're going to start out at one temperature, we're going to end up at the same temperature. So, in that sense, there's no energy change. If we did this adiabatically, then we could expect a delta H change.
Wait, how do you
It depends
know
on how
what
it depends on the volume change, though.
Yeah,
Yeah.
I kind of made note of that. It's like you can't really tell a volume change, so it could be negative or positive depending on if it's 2 moles going
Yeah,
into
it
one,
depends on
or
how
if
it's
it's
mixed,
1 mole
but
going into 2.
If they say figure 19.2, we can go take a look and see how they're mixing it. We can determine it from there.
Yes, 22.
22, all right. Explain why you would expect a reaction of the type AB yields A gas plus B gas always be spontaneous at high rather than at low temperatures. Well, we look, what is delta H for this?
I don't know how to determine delta H.
Well, you should. In order to break a bond, does that cost you energy or does that release energy?
How do you know if we're breaking a bond?
We're breaking a bond. We're breaking A and B apart. And so whatever is holding A and B together, we're breaking that, whether it's ionic bond or
So it's gonna
most
be
likely a
endothermic no
covalent
matter
bond
what.
here. So we're going to break this bond here to form the atomic species. You know, this would be like nitrogen monoxide or carbon monoxide. If we're going to go from carbon monoxide to carbon gas and oxygen gas, we're breaking a bond. In fact, we're going to break a triple bond in that case, right? This is endothermic. And typically you break bonds, right?
Oh.
I mean, whenever you break bonds, it's endothermic. Whenever you form bonds, it's exothermic, right? That's typical, unless the bond is unusually unstable, you know, then, but those are for exotic species.
So that's how we determine delta H.
So delta H is endothermic, so it's unfavorable at low temperatures, but delta S is positive, and so it's favorable at high temperatures. So this is favorable at high temperatures. There's a remark that comes from number 22, and the remark is that molecules cannot exist at high temperature. Molecules cannot exist at high temperature because of this. Delta G is going to convert it into atoms. Okay.
For like 41 or 45, how do we know we're looking for Q rather than K?
41 through 45.
Yay.
Take a look at that.
It's like 41, 42, 43, and 44.
45. Right? Alright.
How do we know we're talking about Q? Is there
41, use thermodynamic data at 298 Kelvin to decide in which direction the reaction is spontaneous when the partial pressures are.
partial
Well,
pressures?
We don't know if these are the equilibrium, right? Pressures or
So
not.
When it states at equilibrium, that's when we look for K.
Yeah, I mean, if these were given at equilibrium, this would be K. This might be K, you know, if these are the equilibrium pressures. We can find out, the way we can find out is we could just use,
G equals G naught plus RT.
right, we can calculate the equilibrium constant from thermodynamic data, that is delta G, you know. Once we know what the K value is, then we can compare that to these. Are these equilibrium or not, just by doing a check, you know, Q versus K type check.
How do we determine if delta G, delta S, or what? I mean, how do you know we're looking for, like, what thermodynamic data do we use? Delta H, delta S, or delta G?
Well, if they're asking if it's spontaneous, then what do you,
Talking about delta G.
they're talking about
Greater than or less than 0.
delta G. But
But entropy is spontaneous too.
you have to look at the entropy of the universe, right? If you look at the entropy of the universe, then you're absolutely correct. Entropy is spontaneous. The entropy of the universe consists of two things. It consists of the entropy of the system plus the entropy of the surroundings. You go back earlier, We talked about the entropy of the surroundings being very difficult to determine because that's the entire universe, other than the reaction you're looking at.
Yeah.
And so we cannot use entropy because the entropy we calculate is the entropy of the system, not the entropy of the universe. And so,
How come is it not with the system only and the universe has to be considered?
well, because our appendix D is too small, we'd have to have everything in appendix D.
So we're looking for delta G.
Right. Delta G is the second law of thermodynamics. Delta G puts it all in terms of the system rather than the surroundings. And we have to use the first law of thermodynamics and actually then the third law of thermodynamics.
I know why can't we look for delta H?
We can. There's nothing that says we can't look for delta H. We can look for delta H, but it's not going to tell you anything. Same thing with delta S of the system. It's not going to tell you anything. The only thing that's going to tell you if it's spontaneous or not is delta G. Because delta G is based on the second law of thermodynamics. Delta H is not. And, you know, if that was a pattern, that is, you know, all exothermic reactions are spontaneous, all endothermic reactions are non-spontaneous, then that would work too, but that isn't the pattern because there are violations of that.
Oh.
Thermodynamics was developed before people, you know, universally accepted atoms and molecules. You know, thermodynamics, people have been trying to disprove thermodynamics, the laws of thermodynamics. You know, what are laws? Laws are based on experiments and observations. Thermodynamics was not derived from theory. It was just based on patterns that people saw. And so people were looking for violations and have been looking for violations or exceptions to the laws of thermodynamics for hundreds of years now, I think, but or not hundreds, you know, over 100 years now, but have not found, right? Not found any. Unlike, you know, the ideal gas law, oh, yeah, people can find violation of that. But thermodynamics is much more substantive. Thermodynamics is an incredibly useful tool for chemists and actually all sciences. But anyway, it's difficult. Use appendix D data to determine Kp at 298 Kelvin. 77?
Oxides of nitrogen.
Oh, 77. Oxides of nitrogen? Oxides of nitrogen are produced in high temperature combustion processes. The essential I did number 77 a little bit, something similar to that the other day. The essential reaction is N2 plus O2 yields 2 NOs. Nitrogen gas and oxygen gas are a fairly unreactive mixture. Unless you're at high temperatures and high pressures, you can't. NO is called NOx, nitrogen monoxide. And so what happens is the air in an automobile engine actually combusts, you know. What happens in an automobile engine is that the temperatures and the pressures are very high, and so it's not just the gasoline that's burning, but it's also the nitrogen that's burning. The nitrogen gets combusted by oxygen. It's very difficult to combust. But we don't want it to react because it forms NO. NO is toxic. NO is a colorless toxic gas. NO is spontaneously oxidized by O2 to NO2, which is a brown gas present in smog. And so this is NOx formation, or oxides of nitrogen. And so different conditions will produce different amounts of NO. And so at what At what approximate temperature will an equal molar mixture N2 and O2 be 1.0% converted into NO? And so equal molar mixture, what does that mean?
1:1.
It could be 1 to 1, or it could be
2 to 2.
2 to 2, or 3 to 3. Just, it's equal, so, you know, we'll just have some initial molarity here, which is going to be the same as the molarity here, so we'll just have the molarity the same.
Excuse me, why are you using the ice table?
Why? Because we use the ice table for any kind of reaction, and this is, how much is 1.0% converted means 1.0% reaction. You know, so we want 1% reaction, and so we use the ice table for that. If we want 1% reaction, how much of my initial am I losing? Yeah, I'm gonna lose 0.01, my initial. And how much am I gonna have left over? 0.99 of my initial. And so this is the same, so I'll have 0.99 of my initial. And over here, this is double, so I'm gonna get 0.02 of my initial. Is that correct?
Yes. This is.
It turns out that, okay, this is Kate, equal molar. Oh. Equal molar, I could do two things here. I could leave it as concentration, because in this chapter, you know, I'm dealing with KEQ, and in this case, KEQ equals what? Equals KP. It's all gases, right? But it's not necessarily equal to KC. Do you guys remember in chapter 15 when KP and KC are equal? What do you need to have in order for KC and KP to be equal? Delta N of gas, right? And so delta N of gas here is 0, so that means RT drops out, equals 1, and then KP and KC are equal.
I remember.
You remember? Okay, this is because delta N of the gas is 0, right? Delta N of gas.
Before it didn't, and now you sparked it. Thank you.
Okay, good. All right, and then we can calculate the KC value, and it just works out. All the units are going to cancel out this here. So this is going to be 0.02 times the initial squared divided by 0.99 times the initial. Actually, this is the same thing, so just square this. So the initial concentration drops out. So this just equals 0.02 over 0.99 squared. And so what is the K value there for this?
If the units still cancel out for the case,
Then the initial concentrations make a difference. You know, if the units don't cancel out, like if these concentrations don't cancel out, then the initial, it's going to depend on your initial concentrations where your final equilibrium is going to end up,
0.0.
like in back in chapter 15. And so in order to solve this problem, you would have to assume, you just say, assuming initial concentration of 1 molar or something like that, and then that would work. You notice they don't even give us the volume, right? They don't give us the volume, so we can't calculate the pressure. But the volume would have canceled out. So anyway, what does it come out to, Kelly?
About 4.0 times 10 to the negative 3.
Okay, give me one more digit.
Negative 4.
4.08
times 10 to the negative 4.
Times 10 to the negative 4?
Yeah.
Okay, 4.08 times 10 to the negative 4.
Oh yeah, that's right.
And so, all we need to do here in this particular problem is
put it into.
But it says use data from appendix D too.
Well, you know, what temperature am I gonna get this? Because I'll tell you, KEQ at 298 Kelvin, let's calculate that. You know, KEQ at 298 Kelvin is equal to what? Let's just, this is an aside, we don't have to do this. Well, we'll just do it for illustration purposes. KEQ at 298 Kelvin under standard conditions is equal to what? Right, e to the negative delta G naught over RT. And so we can calculate this. Okay, this is a formation reaction because we're forming NO from the elements. The only thing is, the formation reaction is defined for the formation of 1 mole of NO. Here we're forming 2 moles of NO. And so we have to double the delta H or delta G of formation of NO. So does anybody have that value? No? All right.
86.55
86.55?
kilojoules.
All right, so delta G of formation for 2 moles of NO. Well, this is it. The delta G for this reaction is equal to the delta G, well, 2 moles times the delta G of formation of NO, minus the reactants. The reactants are going to be 0 and 0 because they're elements. And so it's going to be 2 times, what was it, 85?
86.55.
86.55 kilojoules, which is going to give us
173.10.
which is going to be 173,100 joules. Is this spontaneous or non-spontaneous?
Non-spontaneous.
Is it highly non-spontaneous or
Highly non-spontaneous.
mildly non-spontaneous?
Highly non-spontaneous.
Highly non-spontaneous. So this reaction is not going to go, which is good because if it did go, you know, we'd be in trouble because the room is full of nitrogen and oxygen, and if it's producing a toxic gas, then we're in serious trouble. But let's see, you know, it's highly non-spontaneous, but how much toxic gas do we expect at room temperature? And so we can calculate that by looking at K to determine how much toxic gas we might expect. And so this is going to be minus 173,100 joules divided by 8.3145 joules per Kelvin times 298 Kelvin here. And so
4.56 times 10 to the negative 31st.
times 10 to the negative 31st.
Negligible.
Yeah, so pretty much, is it even going to be anywhere close to 1% converted? No, not even close. It's going to be such a negligible amount of NO, which is good for us. Yeah.
I thought we were going to be in trouble.
Right. We would.
We would all be dead.
It is 1.538 times 10 to the negative 13. That's an extra.
Oh, that's a big difference. 1.3. What is it? 1.
Sorry, I changed.
I was right the first time. Forgive me.
You were right the first
Yeah, I
time.
was right the first time.
All right.
4.56 times 10 to the negative.
Whoa, God, he's all over the place.
Not Scott.
Man,
God,
he's
yeah.
all over the place.
All right. So if we did an ice table with this, we'd get a negligible amount of NO, right? But we can change the driving force, and we can also change K with temperature. And so we just got to figure out at what temperature are we going to get a K value that's equal to this, because this is the K value that we need. We need this one. So if this is the K value that we need, then we just got to figure out the temperature. And so what is that? The temperature is equal to delta G naught over R ln K. Yes?
Would you have to put the expression delta H naught minus?
Yeah, what's wrong with this? Somebody tell me what's wrong with this.
Delta T depends on temperature.
Yeah, and do we know the temperature? Yeah, T is equal to delta H naught over delta S naught minus R ln K. You could memorize that, or you could derive it. You could derive it just by plugging in up here delta H and delta S. You get it in terms of something that doesn't. And so why do we need appendix D? Well, we need appendix D to calculate this, delta H naught. We need appendix D to calculate this, delta S naught. Assuming that delta H naught and delta S naught at this temperature are close to 298.
Did we just assume that we're at standard?
Yeah, we assume that we're under standard conditions because they don't. But do we have to assume that we're under standard conditions? No. Now, this is
Because delta H delta S something.
right. Because are we under standard conditions? No, we're not under standard conditions. The assumption that we're making is we don't assume we're under standard conditions because we aren't. We assume that.
Delta H and delta S something.
Okay. This is okay. This is very tricky. This is very tricky, and I tried to show this earlier. You know where I tried to show it earlier is this. Are we under standard conditions?
No.
No. But now we must be under standard conditions, aren't we? Yeah, we would be under standard conditions here. But now, are we under standard conditions? No, then how can we use something under standard conditions when we're not under standard conditions? Because clearly we're not under standard conditions. How are we using something under standard conditions? Right, well, what we're doing is we're compensating standard conditions for non-standard conditions. So even though we're not under standard conditions, we're using standard conditions because that's what our reference point is and that's what we're going to correct. And so those delta H's and delta S comes from this correction, which we correct, right? And so we don't have to be under standard conditions because we're using those. Yes, we got to use the standard ones, but we don't have to be under standard conditions, which we clearly aren't, because it's a correction to the standard conditions. Right?
So we're looking for delta G naught, delta G naught. Okay. I understand what's with like delta G not being equal to delta G naught. Yeah, I think okay. Delta G is not equal to delta G naught, right?
Well,
is it equal to delta G naught?
okay, now, let's go back to this calculation here. This was the side calculation I did. This is K equilibrium that I calculated. Now, this K equilibrium comes from what? Actually, this K equilibrium comes from, okay, this is going to be the driving force if I start off under standard conditions. You know? If I start off under standard conditions, well, I'm way far off because, you know, I can't sustain 1 bar of NO, 1 bar N2, 1 bar of O2. I can't sustain that. And so it's got to shift. It's got to reverse, right? So that's what I calculate there. This delta G here doesn't have to be under standard conditions. This delta G is whatever you got. whatever I got might already be at equilibrium. You know, I put it up here, and if Q is equal to K, then if Q is equal to K, then delta G is equal to 0. But that doesn't mean delta G naught is equal to 0. If delta G is equal to 0, is that delta G naught equal to 0? Does that mean that delta G naught has to equal 0? No. And so this is why, you know, thermo is
Tricky.
tricky because people don't care about little, you know, standard conditions or other stuff.
There are no restrictions, he said.
And so yeah, and so you have to get it cleared up in your mind. And still, you know, even after you think you get it cleared up, you know, I remember UCLA, I was taking thermodynamics, and the professor kept saying the same statement. You know, he always said, even thermodynamicists don't understand thermodynamics. You know, except for me, of course. That's what he'd say.
Oh, you're expert.
Howard Reese. Actually, Howard Reese is a very famous thermodynamicist. Not that I learned anything in that class. But, so yeah, thermodynamics is not easy. I mean, when you look at the next course after this in thermo, then you'll realize, wow, you barely scraped the surface, you know, because this you would be wishing for these days again, you know, because it wasn't that much, you know, wasn't that much stuff. Because it gets to become a lot more stuff. And so this delta G and delta G naught, you know, you gotta remember these aren't the same thing, but they can be, you know. All right, other questions?
Wait, how come when delta G equals 0, delta G naught doesn't?
Huh? When delta G is equal to 0, delta G naught is not?
Yeah. I don't get that.
It can be. If delta G is 0,
Yes.
and that equals delta G naught, then you know what that tells me?
0. Equilibrium.
If delta G is 0 and delta G naught, that tells me that delta G is equal to delta G naught. That's what it tells me. I mean, in other words, that K is equal to 1. And if I start off under standard conditions, then I'm already at equilibrium. I don't have to go anywhere, right?
Yes.
But if I'm already at standard conditions, then, you know, I already know that the delta G is restricted, and it has to be delta G
No.
naught. Something like that. Not to make it more confusing. All right, other questions on chapter 19?
Any final questions? Please crank them all in.
No final questions? Okay, if something pops up, then go ahead and ask me.
Don't forget that I that. Like I mentioned 3 months ago.
All right, just a note on this slide here. We have the galvanic cells, which we're talking about right now. Later on, we'll talk about electrolytic cells. We could have couples like this. This would be called an oxidation couple because, you know, M is being oxidized to Mn plus. So this is going to generate electrons. This will be the anode couple. the cathode would be just flipped around, you know, M plus going to N. We just read it like that, reactant to product. If we have a couple like this means that there must be a difference in phase here. You know, that is, the reactant phase and the product phase are different. If the reactant phase and the product phase are the same, then we don't separate it by a vertical line. We separate it by a comma. We separate it by a comma. We'll see that here. All right, now let's skip this. Get to where I want to get to. All right, well, how does the E of the cell relate to delta G KEQ? Well, if E of the cell is greater than 0, if you have a positive voltage, that means the reactant is spontaneous. If your battery shows 0 volts, that means it must be dead, you know, at equilibrium. And if it's showing negative volts, the reverse reaction, the reverse of what you thought the reaction is spontaneous. You know, negative voltage and a positive voltage just means, you know, electrons are flowing left to right or right to left. And by convention, we write the anode on the left and the cathode on the right. So if you have a negative voltage, what you should do is you got the anode and cathode mixed up. You should swap them, right? That's the only reason you get a negative voltage in a spontaneous cell.
Okay, well, you got 0 volts. That's because sometimes you didn't put the salt bridge in.
Yes, that could be too. 0 volts would be, but we're assuming the salt bridge is there and everything's set up. The battery's operating. Well, a negative voltage can mean 2 things actually, but in a battery, it just means that you got to swap.
You couldn't get a negative voltage on the spontaneous reaction without switching the cathodes and the anodes.
Well, here, let me show you a negative voltage. Okay. Here we got a negative voltage. Here we got a negative voltage because normally we write this like this. We write the anode on the left, right, and the cathode on the right. And so what we see is that, well, the cathode would be, the oxidizer would be Zn2+. And so the reaction at the cathode should be Zn2+ plus 2 electrons gives us Zn solid. Where do the electrons come from? The electrons are going to come from hydrogen gas. Hydrogen gas is going to give up those electrons and form H+. And so if we set up the cell like this, then, and we connect the voltmeter properly, then what we see is, hey, we're getting a negative voltage. The negative voltage means I misassigned the cathode, right? And the actual cathode is H+. Over here, the cathode reaction. And so what's going to happen now is H+ is going to take the electron and oxidize the zinc. And so when I do this properly, that is, I make this the cathode and this the anode, then the voltage goes positive. Does that make sense? And so it's just a point of reference, because you can always make the voltage positive by just swapping the leads. Right?
I guess I was more asking about like the lab we were doing, and you were asking us to change the concentrations to get it go.
Oh, to go negative?
Yeah.
Right, right. So, okay, in the cell in the lab, I asked you to try to change the voltage from positive to negative. In other words, I tried to, the cathode was on the right, and what I tried to get you to do is to swap it so that the cathode is now on the left, and then the electrons will want to flow the opposite direction. The way I asked you to do that is by strength in numbers. Strength in numbers is like this. H+ is more powerful oxidizer than zinc, so if there's a tug of war, H+ is going to win. However, we can severely handicap the H+ by making its concentration so small, and then give a boost to Zn2+ by making its concentration so big. And by doing that, then all of a sudden we can swap it so that the Zn2 plus now is the cathode. Does that make sense? And so that's what I was trying to have you do in lab. But was anybody successful? You guys got close.
but not past 0.
Right.
It was like 0.02 or something.
Right.
0.2.
Well, that was good because that's the best I saw that day. I think most people didn't even maybe try that particular one, but it's okay. Anyway, if we look at this force, it turns out, you know, the pressure or the force on the electron and the number Z times F is the amount of charge that passes through or the number of electrons that passes through the wire. So you're pushing electrons through the wire. Pushing electrons through the wire takes work, right? And so this would be the equation for electrical work, where Z is like the number of moles of electrons you have, F is the charge per mole, F is called the Faraday, and so Z times F gives you the amount of charge, Coulombic charge. In other words, it's proportional to the number of electrons. And so the amount of work depends on how much charge, you know, or the charge carriers you want to push through there. And so that's where we get this equation from. But the work, oh, here's the Faraday constant. This is Faraday here. The Faraday constant is this. If you have a mole of electrons, the total Coulombic charge is 96,485 coulombs per mole of electrons. The charge on a single electron was back in chapter 2. Do you remember the charge on a single electron?
It's 10 to the negative 23 or something like that. No,
Yeah.
it's not really
10 to the
like
negative
that.
19.
Right, it's like 1.67 or something times 10 to the negative 19, negative 1.67 times 10. That's such a pain that we just call it negative 1 unit of charge, right? It's
Yeah,
quantized.
602 times 10 to the negative 19.
Oh, 602, thank you. Okay. All right, and so the work, well, what delta G is the free energy, and the free energy is the total amount of energy available to do work. And so what we can do is we can equate those, the electrical work that's done to delta G. And so delta G is going to be equal to minus ZFE of the cell, where Z, a lot of people use N instead of Z, N just stands for number of moles of electrons. And so minus NFE is very common, but I don't know why Petrucci switched, because he used to use N too, and then suddenly switched to Z. When products are in their standard states, then it's going to be, of course, standard conditions. So this would be the standard free energy change. This would be the standard cell potential. And so this equation we're going to use to relate E of the cell to delta G, and so this is it here. Typically, we would have to measure. If we're under non-standard conditions, we'd have to measure it. If we're under standard conditions, we don't have to measure it. Because if we're under standard conditions, our redox chart has the reduction potential. And from the reduction potential, we can figure out the oxidation potential just by reversing that reaction and changing the sign. And so we have the oxidation potentials and the reduction potentials off the redox chart. And so we can always calculate E naught of the cell, because those are standard reduction potentials up there. We can get the standard oxidation potentials. And so under standard conditions, we don't have to measure anything. We just calculate the cell potential. We know what F is, and we have to figure out Z, the mole. Now this is why, now I got why Petrucci calls it Z. Petrucci calls it Z because it's the number of moles of electrons transferred in the balanced redox reaction. And so it's not just, usually it's just any old moles, but when we're doing a delta G of reaction, it's going to be the number of moles of electrons in that balanced chemical reaction that are transferred. And so we can calculate our delta G naught easily. Now, if we want delta G under non-standard conditions, where are we going to get E of the cell? Do we have non-standard cell potential, reduction potential? No. Even in appendix D, we don't have it. And so here we'd have to measure E of the cell in order to get delta G, right? Or we'd have to be given an E of the cell. Okay, now, these reduction potentials, let's say, you know, in Appendix D, I have this reduction potential. Iron 2 plus 2 electrons gives iron. This reduction potential here is given as negative 0.440 volts, which means what? Well, if you read this, negative 0.440 volts, does it mean the electrons are going backwards?
It's going from anode to cathode.
No. Only E of the cell has an absolute meaning like that. Reduction potentials and oxidation potentials are arbitrarily referenced to hydrogen. And so if you see a negative voltage like this means that it's it means it's 0.44 volts worse than H plus as an oxidizer. And so iron 2 is worse than hydrogen ions, but iron 3 is
Better.
significantly better oxidizer, you know, by 0.771 volts, stronger oxidizer than H plus. And so that's what the negative and the positive mean when we're looking at half potentials.
You say the reverse for the reduction oxidation.
Right. If we were to look at reducing agents now, what's a better reducing agent, iron or iron 2 plus? If we're looking at reducing agents, we have to reverse this reaction. If we reverse this reaction, then what do we do to the E's? We flip the sign. And so if we're looking at reducing agents, then iron metal has a oxidation potential, and the couple would be like this. It'd be iron to iron 2 plus. Okay? And so it'd just be flipped. Would have an oxidation potential of plus 0.44 volts. Whereas the iron 2 plus would have an oxidation potential of negative 0.771 volts. And so when we look at those numbers, it tells me that iron is a much more powerful reducer than iron 2 plus by about, you know, by about 1.1 volts, right? Much better. And iron 2 plus is better than hydrogen gas, H2 gas, where, I mean, iron metal is better than hydrogen gas, but iron 2 plus is worse than hydrogen gas, because hydrogen gas would be zero.
Arbitrary zero.
Arbitrary zero. Okay, now we don't, you know, want to have to measure everything. What about this? What if I had a couple like this? I want to reduce iron 3 all the way to iron metal. If I want to go iron 3 to all the way to iron metal, maybe I could just add these two reactions together. Yes, that's true. I could add those two reactions together. I get the net reaction that's desired. But can I add the potentials
I
together?
think so from the
We gotta
beginning.
multiply it.
You gave me the
Nah.
answer.
No, we can't, unfortunately, add the potentials together.
What do we do?
We have to convert those potentials into delta G naught values, and then we could add the energies together here.
And then reconvert
Yeah.
to voltage, right?
Yeah.
What a pain.
Yeah. Well, the cell potentials are also tricky in this sense. If I had 1 gallon of iron 2 plus, let's say, as a reducer, versus 2 gallons of iron 2 plus, does that double the voltage?
No.
1 gallon of iron 2 plus versus 2 gallons of iron 2 plus. Or let's think about it this way. If I'm looking at oxidizers, iron 3 plus is a better oxidizer. If I had 1 gallon of iron 3 plus versus 2 gallons of iron 3 plus, is 2 gallons twice the voltage, twice the oxidizing ability, twice as powerful? Is it twice as powerful?
It's more powerful.
Is it? Yeah. Is it double the power? So if I have 1 gallon versus 2 gallons, is it double the power?
In batteries, it works that way, like 1.5 volts to 3
It's
volts.
double the energy, but is it double the power? Let's say the same goes with this. You know, AA or AAA batteries, those are tiny, right? if I have a D cell and D cell's 3 times bigger, then D cell's got to have 3 times the voltage because it's 3 times bigger. Is that true or false? It's false. It doesn't matter because it depends on the concentration. And so the concentration is the same. The concentration doesn't change. If I have 1 gallon of 1 molar iron 3 plus versus 2 gallons of 1 molar iron 3 plus, it's 1 molar iron 3 plus. It's still the same. And so it's going to have the same voltage. It's just going to last twice as long, right? And so that's why you want a D cell or something like that, because it'll last longer, but it's going to have the exact same voltage as a AAA battery, because the chemicals and the concentrations are all the same. Right? And so that's different versus, delta G, if I had, let's say, if I had 2 moles of iron 3 plus at 1 molar concentration versus 1 mole of iron 3 plus at 1 molar concentration, then I'm going to get twice as much energy. Do you see that? Because the amount, it depends on the amount, not the concentration. Whereas the voltage is going to depend on the concentration. How many iron 3 pluses are pulling on the electrons? Okay.
Okay,
Per unit volume.
Is there an equation that relates delta G with voltage?
Yeah, this equation here. This is voltage. Yeah.
Yes.
This is delta G. There's an equation that relates it. For the half reactions, is a little bit more tricky. We didn't calculate. That's for the cell reaction. These half reactions have to be determined. We can't use that. For example, we can't use that equation to calculate this. This is delta G for the reaction. Well, the earlier equation was. This is not a reaction. This is a half reaction. And so we get this by a different way. Using
How do we
Hess's
get
law.
delta G then?
Well, let's take a look. Okay. Well, let me take that back. Actually, if we have the delta G or the E, we can get it here, whether it's half reaction or not. So how do we get it? Well, we have the E, we have the F, and we have Z, but now it's N, but Petrucci was switching back and forth from N and Z, so you should be able to do as well. Well, N or Z will be the number of moles of electrons transferred in the balanced redox. Well, this is going to be the balanced redox, so we see that the 3 moles of electrons transferred. So that would be here, 3 moles of electrons. And then the Faraday constant's given before, 96,485 coulombs per mole. And then we plug it in here. Now, the units are kind of funky, because what are the units going to be here? Well, this is 3 moles, and so the moles cancel out. And it looks like it's going to be in terms of volts per coulomb. You know what a volt per coulomb is? A joule.
A joule, yeah.
A joule. Or it should, well, no, a volt per coulomb, actually not a volt per coulomb. Up here, this would be, if we have a coulomb here, coulomb times a volt is equal to, what is going on here? All the units are screwed up. I see. Yeah. Yeah, there's something wrong with this. Sorry, I didn't catch that earlier. But we'll do it. We'll do a calculation for this, so it won't be. But just make a note that slide 20 is messed up. What did they mess up here? Does somebody see what they messed up? So this should be joule plus joules should yield.
Sure.
Why? Okay.
Oh, that made me confused. Like,
Well, Well, this is in joules. This is small numbers. This is the half reactions. So this is going to be joules, and it's relative to an arbitrary 0, which is the hydrogen. So they're going to be off in a way. And so anyway, this should be joules. And a joule is going to equal Coulomb times a volt. Joule equals a Coulomb times a volt. And so if I have, this should be joules divided by coulombs is going to give me, yeah, joules divided by coulombs gives me volts. Then now it works out.
I can find the delta G here. Those just given or did you?
Those were given. Yeah, yeah, we aren't going to. Well, maybe they solved it. They could have solved this because delta G naught is equal to negative NFE. So N here would be 2. F is 96,485 coulombs. Oh, and E is this. Well, we aren't going to do this. Actually, this particular calculation. We aren't going to combine half reactions. But that's what you do for combining half reactions. Well, we know that delta G less than 0 is spontaneous. Therefore, we know delta G of the cell is equal to minus NFE, so they're opposite in sign. And E naught of the cell greater than 0 is spontaneous. E naught equal 0 is at equilibrium, and E naught less than 0, we expect the reverse reaction to be spontaneous. We talked about this. Let's take a look at what we can do with some of these, and some of this is we can just look at what's going to be spontaneous here. And so if we're looking at metals reacting with H+, H+ is the oxidizer, the metal will be the reducer. Then what we want is we want the oxidation potential here, this will be the oxidation potential, combined with the reduction potential here, should give us a cell potential greater than 0 volts. And that means it's spontaneous. And so what this says is that any metal will react with H+ as long as its oxidation potential is greater than 0 volts. Well, Petrucci doesn't like to use oxidation potential. He likes to frame things in terms of reduction potential. And so rather than just saying the oxidation potential is greater than 0 volts, he says that the negative of the reduction potential, is the oxidation potential. Right? And so then that would be it. And so I did this a long time ago, but we didn't use the numbers. We just used the chart here. And so we said this. We said that H+ is capable of oxidizing any reducing agent more powerful than hydrogen. Any reducing agent less powerful than hydrogen will not be oxidized. So for example, copper metal will not be oxidized. Okay, so what he's saying here is this. All right, H+ has a reduction potential of 0 volts. Copper has an oxidation potential of, well, what is the oxidation potential of copper?
Negative.
It's going to be negative 0.34 volts. Right? That would be the oxidation potential of copper. Now, why don't I follow Petrucci the way he does it? The reason I don't like to do the negative of the reduction potential is this. Because the higher the oxidation potential, that is, the more positive the oxidation potential is, the more likely it is to be oxidized. Okay? And so it's very simple. You look at the number. The higher the oxidation potential, the more likely it is to be oxidized. And so what has the lowest oxidation potential on this chart? And what has the highest oxidation potential? Well, the highest oxidation potential is going to be positive 3 volts. And that's going to be lithium. The lowest oxidation potential is going to be negative 2.8 volts. And that's going to be fluoride. So fluoride is going to be the species that's hardest to oxidize because it has the lowest oxidation potential. Okay. Lithium is going to be the easiest to oxidize because it has the highest oxidation potential. And that's based on the arbitrary 0 point of hydrogen. You know, what they should have done was they should have made an absolute zero. The absolute zero, what would be the absolute zero of reducing agent? Do you think fluoride is the absolute zero? If fluoride were the absolute zero of reducing agents, if we made fluoride 0 rather than negative 2.8, wouldn't that be easier? Then everything would be positive in reference to our absolute zero, fluoride. But do you think fluoride is the absolute worst reducing agent out there?
No.
No, they're much worse, right? Much worse.
How about sulfides?
Sulfides are good reducing agents. Sulfides are really good reducing
How about
agents.
superacids?
Well, I mean, there's lots of things you can think of that, and so the problem is we don't know what the absolute worst. Does anybody know what the absolute worst reducing agent is?
Water.
No, so maybe, and if somebody found it, somebody would try to make one even worse, right? And so it's one of these targets that are very difficult. And this is kind of like what's going on with the absolute internal energy and absolute enthalpies. You know, you don't know what the absolute zero of potential energy is. Okay, now let's look at reduction potential. What has the highest reduction potential? Fluorine has the highest reduction potential, which means that it's the species that's most easily reduced. What species has the lowest reduction potential? Not lithium. Lithium ion, right? Lithium ion has the lowest, which is minus 3 volts, which means that lithium ion is very difficult to reduce. Now, the sign always confuses people because some people will think, well, lithium ion, since it's negative 3 volts, means it must be an oxidizer, not, well, it is an oxidizer. It must be a reducer, you know, not an oxidizer. Or the reaction flips. No, it's just based on the arbitrary 0 of hydrogen. Yeah. And so you should know. Now, what makes a good battery? What makes a good battery is the highest oxidation potential combined with the lowest reduction potential.
Wouldn't that give the biggest swing?
That's why
What
there's
would make
lithium-ion
a good battery?
Depends.
Lithium.
Different power or
A high, you want high voltage. Let's say we want high voltage. Do we want a high oxidation potential and a low reduction potential? Or do we want a high oxidation potential and a high reduction potential? Or do we want a low oxidation potential and a low reduction potential? What would make the highest voltage?
The strongest and the weakest together.
No, the strongest and the strongest. And so this is why I write E of the cell is equal to the oxidation potential plus the reduction potential. The highest oxidation potential we have, we're going to have the strongest reducer, right? The most easily oxidized species, like lithium. The highest reduction potential we have, we're going to have the strongest oxidizer, like fluorine. And so that's going to yield the highest voltage. So what we want is, if we want to maximize the cell voltage, then we want the highest oxidation and the highest reduction potential. That's going to give us the strongest battery, and that's why I add them. I don't like to subtract them because subtracting them gets people confused, you know, because then they want the highest on one, but they want the lowest on the other. Well, that doesn't make sense. You want the highest for both. Okay? And that's going to give you the highest voltage.
How how would it give you the highest voltage? I don't really see it. Just take the number.
Well, tell me what the highest reduction potential on this chart is.
Reduction potential?
Yeah, the highest reduction potential on this chart.
Negative 3.0401.
No. You can try again. The highest reduction potential.
The highest?
Yes, the highest reduction potential.
2.866.
Okay, 2.866 volts. That's what's the couple? That's fluorine goes to fluoride.
Uh-huh.
Okay, what's the highest reduction potential on this chart?
I mean lowest.
No, the highest reduction potential. What is the highest reduction potential on this chart?
Negative 3.04.
No. Try again. Oh. Highest, no, sorry. That's why I'm confused. Sorry, Kelly. What is the highest reduction potential on this chart?
Highest reduction?
Yes, highest reduction potential.
That's fluoride.
Still.
Oh, I still think it again.
You're still doing it. You're still
This
doing
one.
it.
I want this one. The highest oxidation potential on this chart.
If it's the lowest, if it's the
All
lowest
right,
reduction
yeah,
potential,
all
it
right.
must be lithium.
But anyway, if I confuse you like this and you still have it straight, then you understand it. That's good.
Oh
So what has the what has the highest oxidation potential?
no! Lithium!
Lithium, right? And what is the voltage?
Negative 3.040.
Is it negative or positive?
It's positive
Yeah.
because the reduction is negative.
Right? And so these are this. Lithium goes to lithium plus, fluorine goes to fluoride. If I add these together, I'm going to get
5.7 volts.
5.906 volts. That's the highest voltage battery I can make from this. And this is a huge driving force. If you look at the delta G for this, it's very negative.
Thousands of kilojoules.
No, it's
So it
not
really wants
thousands
to
of
go forward.
It really wants to go forward. Lithium and fluorine will make a very violent explosion, right? Lithium and fluorine. So this battery would be very difficult to construct, but this would give you the highest voltage. But you might think, well, I've seen higher voltage, like a motorcycle battery, 6 volts. Well, maybe this is in your motorcycle.
Significantly high.
Or a car battery is 12 volts. So how do you get a car battery? Well, you know, both motorcycle batteries and car batteries are actually
Oxidation reduction reaction.
no. They just what they do is they put a whole bunch of little batteries together to make a big
Also,
battery.
this gives you
Wow.
Much more.
Yeah.
use.
And so car batteries actually consist of 6 batteries, and they connect them together, and then the voltages add up. They connect them in what they call series. You can also connect them in parallel, but if you connect them in series, then 2 volts plus 2 volts, etc., gives you 12 volts. Mm-hmm.
Then why is there lithium-ion batteries?
Well, it depends on what they're mixed with.
Yeah.
They don't have to be mixed with fluorine.
There's actually different battery designs. There aren't. What we're looking at are these are wet cells. You know, they're
Wet cells.
wet cells. They're aqueous. You know, wet cells are very heavy. Like if you're they carry a battery, very heavy, and they require water,
Car batteries
and they
are
have
wet cells,
limited operating range. 'Cause if it gets too cold or too hot, if it gets too hot, your water could boil. If it gets too cold, your solution can freeze. And so it's very limited. And so people are looking at other kinds of batteries that have a wider operating range or more specialized. You know. And so lithium-ion batteries are totally different design than this. We'll see it later.
With this transfer of electrons, it is also affected by temperature. Like if you froze that lithium fluorine battery, it would slow the reaction.
Oh yeah.
Because you said it was based on concentration.
Yeah, the state is going to be. All right, so let's see how much we got here. Oh, okay. So it's easy to add these up. What you do is this: if you have a chart like this, copper 2 is capable of oxidizing what? Is copper 2 capable of oxidizing copper? Well, not really, because you form the same thing.
We're just gonna go back.
Is copper 2 capable of oxidizing iodide? No, because iodide is even worse of a reducer than copper. And so copper 2 is capable of oxidizing any reducing agent stronger than copper. And so all these down here. And so what that means is that if I add the copper 2 is plus 0.34 volts. With any of these down here, and so I have to flip it and change the sign. These are all going to result in a spontaneous cell. And so 0.34 volts, it can oxidize SO2 because that would go negative 0.17. It could oxidize this tin 2. This would be negative 0.154. So 0.34 positive minus 0.154 will still give me a positive voltage. Whereas if I try to oxidize something more difficult, and so this is positive 0.34, and then this is going to, if I reverse this one, it'll be negative 0.53. And so positive 0.34 plus a negative 0.53 is going to be non-spontaneous.
It's going to be.
And so, you know, this pattern, we can use the numbers to actually calculate how non-spontaneous or how spontaneous that's going to be, or what kind of voltage we'll get, you know. And so, of course, the bigger or the farther apart these become, the larger the voltage is.
That'll be an electrolytic cell.
Yeah, that could be an electrolytic cell, right. And so here, metals with negative reduction potentials react with mineral acids. Mineral acids, it should be. What's the difference between a mineral acid and an oxidizing acid? Let me show you. Mineral acid just has H plus as the oxidizer, the anion is a spectator. Oxidizing acids, the anion is not a spectator. And so, for example, sulfuric acid is considered an oxidizing acid because sulfate is a more powerful oxidizer in combination with H plus than H plus alone. Nitric acid is considered a oxidizing acid down here. You know, the nitric acid is capable of oxidizing a lot more metals than mineral acids are. And so this little general rule of thumb is wrong for it's not with all acids, it's with mineral acids or non-oxidizing acids. All acids are oxidizers then. All right, now if delta G naught is related to E, then we know delta G naught is also related to KEQ. And so we can see that we can connect these three. We can connect delta G, KEQ, and E the cell.
Wow.
Yeah. And so if you want an equation that tells us, this would be E naught of the cell going straight to, or KEQ, or KEQ going straight to E naught of the cell. Or you could do it in two steps. You know, you could go from E naught of the cell to delta G, and then delta G to KEQ, or you can just combine the equations and do it in one step. But when we combine the equations, we always have to be careful because, you know, this E naught of the cell, what is it, 298? That means KEQ will be at 298, or better be at 298. If you have a KEQ at 600, then it's a different story. This equation we aren't going to use yet. So this equation, just ignore that equation. We use another equation that looks very similar to that. And so here, you know, this tells all the ways now we can determine some of these thermodynamic factors. We can measure the equilibrium concentrations or equilibrium pressures to determine K. So this is experimental. Experimentally, we can measure the cell voltage using a voltmeter. Or we can calculate these things theoretically. We can calculate them theoretically just by going into the book, Appendix D. Appendix D data comes from calorimetry. And then the heat capacity measurements to get the S. So this doesn't require an experiment because we get this from Appendix D. From Appendix D, we can get delta G. Once we have delta G, we can either figure out what the cell voltage is going to be, or we can figure out what the equilibrium constant is going to be. Those are for standard conditions, but the battery it's funny to be under standard conditions, because under standard conditions, what you have to have is you have to have product there to begin with. And the more product you have, the lower the voltage. And so it's very funny to be under standard conditions. Once the battery starts operating, then we're going to deviate. And so here you can see a battery in operation. The reactant concentration goes down, the product concentration goes up, and what happens is the voltage decreases. We know that under non-standard conditions, our delta G is equal to delta G naught minus RT ln of Q. Well, we can use the relationships between delta G and E.
Why does it show a decrease?
When you operate a battery, the voltage just decreases because the reactant concentration goes down and the product concentrations go up. In other words, as you build up more product, less of a driving force. Or you can understand it based on Q. As Q becomes bigger, Q is going to get bigger because we're generating more product, less reactant. So Q is going to continue to grow as the reaction proceeds. As Q gets bigger, what's that going to do to our...
Negative's going to get bigger, or the more negative. Yeah, more negative.
It's going to get more negative?
Well, the G's got to get smaller because of the larger negative.
Yeah. Well, this is going to get more negative, but what's it going to do to our, actually, let me explain this with a calculation. It'll probably be easier to see that way. We can see a calculation here because of this. We know that delta G can be related to minus ZFE, delta G naught to minus ZFE naught of the cell. And so we can relate E cell to E naught of the cell. This is called the Nernst equation here. So E of the cell is equal to E naught of the cell minus RT over ZF ln of Q.
Negative RT?
Okay, but what we're going to do is we're going to get rid of the natural log. We're going to convert that into log base 10. This is easier that way. And then R is a constant. And temperature, what temperature are we at? 298. And in this particular equation, we're going to fix the temperature 298. Temperature is always going to be at 298. And so in this case, we could have called it standard temperature because we don't deviate. And so R times T divided by F, RT and F are constants, equals 0.0592 volts. Z changes depending on the reaction. And so 0.0592 volts is only at 298. All right, now let's see. As Q gets bigger here, what happens to log of Q? That becomes bigger. And as this term becomes bigger, this becomes more negative, which means that the cell potential goes down. So the voltage is going to be going down.
The nerd equation.
Yeah, this is an error. Do you see the error here? Unfortunately, I didn't check these slides. I just copied the slides or downloaded the slides off the site. But do you see the error here?
What?
It should have worked here, but delta G is equal to delta G naught plus RT ln of Q. And so then it makes sense. As this gets bigger, then delta G becomes more positive, right? Anyway, this allows us to calculate under non-standard conditions at 298 Kelvin. And this is a very famous Nernst equation. And so we can calculate any voltage here if we know that. So we set up an ice table. We'll do that next time. Do this. We might, it depends on how far I get through chapter 20. Our next test, which is going to be a week from tomorrow, might not include all of chapter 20. If it doesn't, then you don't have to do all the homework for chapter 20. It depends on how far I get on Monday. I'm not gonna do that.